Hi there, I'm Stephan Lavavej, Visual C++ Libraries developer, and welcome back to Core C++ Part 7. In this part, I'll be covering the usual arithmetic conversions in C++, which are a source of great pain and misery every once in a while. But in addition, I'll also be showing a bit of template metaprogramming for people who like very high-level rather than low-level things in the core language. I'll also be going through a bit of our STL implementation, as well as a current build that I've got on my machine that has not yet been released. It's got some interesting things. So the usual arithmetic conversions, let me put those off to the side here. Let me start by how I came to explore this area deeply recently. There was a bug in the STL. Our STL implementation is extremely high quality, and it also tries to be extremely fast. And sometimes these are in conflict. Implementing optimizations, if they're not done with extreme care, can actually introduce subtle correctness bugs. And this one had actually been around for a while, many years in fact, until users reported it, and we were able to fix it in our current builds. So what does the bug look like? Well, let's look at the algorithm library in the STL. We've got std_find over here. I'm just using the STL as a motivating example, even though this series is about the core language. So std_find is very simple. It goes through a range of iterators, but they can be raw pointers. And actually, in this example, I will be using raw pointers. And it says, OK, for every element in the range from first to last, is there one that is equal to some specified value? And if there is, then return an iterator or a pointer, if we're working with raw pointers, to this element. So this is specified just in terms of equality. Very, very simple. So let's look at a program. Here I've actually contrived this program to trigger the bug. Fortunately, the bug was quite difficult to trigger because it relied on a certain set of circumstances properly aligning. So here I'm including all the headers I need. I'm also printing out my compiler version to make sure I don't get confused when I switch between VC11 RTM here and my current build of the Milan compiler plus libraries. So I'd love to be able to just construct a vector from an initializer list, but we didn't have that in VC11. So I'm going to have a vector of signed char. This is a signed 8-bit type. And I'm just going to push back 11, 22, 33, 44, 55. Then, to trigger the bug, I am going to get pointers to const signed chars. I can use the C++11 member function data to get a pointer to the first element of the vector, which is contiguous. And then if I say vdata plus vsize, I'll get a pointer to the end of the vector, one past the end as usual. And then I'm going to call std_find from the algorithm header with first and last. I'm just going to look for the value 33, which is conveniently right here at index 0, 1, 2. So I would expect to see, if I subtract the first iterator, the index 2 printed. So let's try compiling this with VC11 RTM here. This font is small, but this is not the especially interesting one. So if I run my kitty program here, it prints out VC11 RTM's version, and I get 2, as expected. You can try this out for yourself, and you'll see exactly what I'm seeing here. So this is very close to triggering the bug. Let's look at the bug here. So imagine in here I've got something like, actually let's stomp over this value. Let's suppose I've got a -1. This is a vector of signed char, which can represent -128 through 127 inclusive. So -1 is totally legitimate. And let's actually search for -1. Okay, so this should find index 0, 1, 2, 3. So let's save and compile this. And if I compile and run, I get index 3 printed as expected. Now, let's suppose I search for some bogus value, like the number 255. Okay, let's go back to the specification of find. Find takes these input iterators, in this case it's pointers to signed chars, and it takes a t value of a possibly different type. And it's just supposed to search for the expression element equal value. So we know, I don't even need to write an example, that if I have a signed char equal to -1 and I try to compare that with equality to just the integer 255 here, this is of type int, that's going to be false because -1, the signed char, is not equal to 255. So this find should not find it in the range. I should get the index 5 reported, which is one past the end of my 5-element vector. But with VC11 RTM, let me save this here, searching for -1. No, this is not the window that I want. Here we go. Let me compile and run. Instead of getting the index 5, I'm getting the index 3. This says that I found the number 255, and by the way, it's this -1. So apparently, our C++ standard library implementation believes that -1 signed char is equal to 255 int. That's false. So this is bad. This is actually kind of bad because this is a runtime correctness problem. Of the bugs we have in the STL, usually they're like something weird doesn't compile, and that's not too bad. But if something compiles and you can ship that to your customers, your users, and then it just doesn't work, that's extremely bad. So what was triggering this bug? Well, let's debug into this and see what's going on. So I have compiled with debug info, so I can, from this command line, type devenv run kitty.exe, and by the way, open up my kitty CPP, and this will launch the IDE, even though I didn't build it in the IDE. The reason I'm doing this is because when I use Milan, I'm going to need to build in my command line. So here I've got my program in a nice big font. Let's debug into this find call, because everything before this is going to work fine. So let's go in, and I need to bounce. Oh, I was using raw pointer, so I don't even need begin end. Okay, so here is a call to stood find, first last, and here you can see we're in our STL internal header X utility. So after some debugging logic, let us jump in and out of these helper functions. Okay, so now we're in this helper function _capital find. You can tell it's internal because it's ugly. _capital means users can't mention this. And we've got this overload, this funny overload here, taking const sign char stars and int. You'll notice these are exactly the types that I specified. If I had specified any other types, like stood strings or whatever, or a list of stood strings, it would have gone to this generic implementation above here that literally says lm == val. This is always correct. This is extremely hard to screw up. But then we've got these other overloads for const char star, const sign char star, and const unsigned char star. By the way, these are 3 distinct types in the core language. Char is unique this way for all other types, like int is equal to signed int. But char is actually distinct. I could go into this whole story. So here we've got const sign char, and we've got this dedicated overload. So why are we doing this? In general, we don't like having extra code in our headers because it's more to maintain, it's verbose, we like to centralize things. But in this case, this implementation is trying to be tricky. It's going to call memchar, this function from the CRT. And then it's going to do a bit of a dance and then return a pointer. So why are we calling memchar? Let's go over to the C standard. So memchar is this function from the C standard library, and of course it's very low level. It takes a const void star, it takes an int, it takes a number of bytes, and it locates the first byte in this range that is equivalent to this other byte. The reason why this exists in the CRT, which has actually very few algorithms, is back then, the programmers took what they could get, and also memchar, like memcopy and memmove and a couple other functions, can actually be implemented faster in assembly than in just plain old C or C++. You can spam out certain assembly instructions that can very, very quickly on certain processors find a particular byte in a range without writing an actual loop that the compiler has to go through. So that's why this exists. So because the CRT may have, and in fact does, have a special assembly implementation of this, in the STL in stood find, we would like to detect when the user is giving us raw pointers to a range of bytes, either char, signed char, or unsigned char, and call memchar at compile time using our fancy template metaprogramming. So this is cool, except when it's not. And the bug here is that find is specified differently than memchar. And aside from the fact of their return values, because find and memchar disagree on what should happen when we don't find the value. We were correctly handling that. But find here is specified in terms of value equality, whether one value of this type in the range is equal to this other t that the user has given us. Whereas memchar in the CRT, it is not specified in terms of value equality, it's specified in terms of byte equality. It takes this const void star and it's interpreting them as unsigned chars, and then it takes an int c, interprets that as an unsigned char, and it just says, hey, byte, are you equal to this other byte? Cool. So these semantics are different, and our implementation, let me go here, was not correctly handling this. So here you can see with this background information, this special overload taking consign char star first, consign char star last, and int val, passes the val directly to memchar, regardless of its actual value. So in this case, in my program here, the value int, and 255 is a totally cool int, is outside the range of scient char, which goes from -128 to 127 inclusive. So there's no way that it could possibly be found in this range. And yet, we were passing it directly to memchar in an attempt to be fast. So this then goes for byte equality. And the byte 255, which is all 1 bits, FFF, or yeah, just 2 Fs, is equal to the byte -1, interpreted as an unsigned char. So memchar is like, hey, these are totally equal. This is an index 4. And stdfind should say, no, these values are totally not equal, you know. So we should return the end iterator. So this means that we need to do something different, template metaprogramming-wise. But then this usual arithmetic conversions will step in. So let's now switch over to this Milan build I've got, where we've got the fix that was checked in a couple months ago. Okay, so let's stop debugging this. Okay. And okay, so I'm still going to need this to debug. By the way, here I'm including vector, but if I'm going over to the Milan build, I no longer need to push back this stuff. Let me put a -1 here and uncomment this. Now you can see I can actually construct from an initializer list. Let's go to my Milan build. And I'm printing out the compiler version to make sure I'm not screwing something up. Let's compile. And awesome, we actually compiled with this initializer list. You can see in my local build, we have added initializer list constructors to std_vector and the other containers. We still got to fix up a few more places. That has not yet shipped, but it will ship at some point in the unspecified future. So let's run Kitty here. You can see it's printing out my compiler version, which indicates I'm running this actual correct thing. And I searched for the value 255 in a vector of scient char containing a -1. VC11 RTM would have said, oh, I totally found it. It's at index 0, 1, 2, 3. And this current build I have says, oh no, these values are totally different. I'm finding it not at all, and I'm going to return you a pointer to the end of the sequence at index 5. So this is correct. This is what we would like to see. And in fact, I could throw any types of the range or the value here, and it would always get the right answer, which is cool. So how do we achieve this? Did I simply rip out this memchar optimization, which I could have, and that would have restored correctness, but it would have lost our fancy optimization. And I actually did not do that. I actually achieved both correctness and performance. Let's debug into this thing. Let's now use VC11 RTM to debug into this executable that I built with my local Milan build. So let's put a breakpoint here. And you can see I can totally debug even though I've got this init list, although if I tried to compile here, it would totally fail. Okay, so put a breakpoint, and now let's step in. Okay, now we're going to get to the usual arithmetic conversions. It's going to be fun. So here in my X utility in my local build, here's the external stdfind that the user, me, is calling. I do some debugging logic, and then I jump through some wrappers. These are all doing useful things. And then here, I've got a different function, internal _ find, with different guts. You can see I'm doing some template metaprogramming here. So I'm going to go through that pretty quickly. I'm taking these iterators here and some value. I don't know at first what the iterators are, what the value is, and I want to activate my memchar optimization under a very specific set of circumstances. And here I'm actually writing it out at compile time in code. I'm saying, okay, let's look at this iterator. And there's 6 iterators that I could possibly match against. I want raw pointers to either char, signed char, or unsigned char, and I don't actually mind if they're const or not const. So I could specify this in a bunch of ways. I'm just going to say 6 different is_same tests and OR them together. So if my iterator is any of these, then the range coming in is bytes, and I like bytes. But I also need to look at the value, because what if this value is something like a user-defined class that has an overloaded operator equal? I can't possibly feed that thing to memchar. Or like, what if it's a double, you know, something bizarre. I only want integers as my values. So if this given tie is an integral type, then I can activate my optimization. The stars have aligned, and I know that if I do extra tests, I can actually activate my memchar optimization. So I'm going to use tag dispatch, pass this to my other helper to indicate should I activate the optimization or not. If this logic here said no, these are like list iterators or stood strings or user-defined classes, then I get false type. And that means I need to use the handwritten algorithm by the standard library implementer saying equal equal. That's always correct and in fact is the best we can do. However, if the stars align, then we need to be a little careful. We need to do this range check that I talked about. Okay, we're getting very close to where the usual arithmetic conversions will matter. So I've got some helper function. I haven't showed you that yet. This is where the fun really happens. And I'm going to test. Okay, given the type of the elements, here I'm encoding that in first, and the particular value, if that value is not within the limits of these bytes, which is either -128 to 127 or 0 to 255, then if value is not within that range, it cannot possibly match any of these elements. That means that I don't even need to do any comparisons. I can just return the answer in constant time and say, hey, I didn't find it last. So this is actually a super optimization. I got order 1 instead of order n. That probably won't activate too often, but it's necessary in order to catch cases like this repro here, where the incoming value, 255, is simply outside the possible range of signed chars. So this within limits check will detect that. So if I verified that the element type is good, that the value type is good, and that the value is actually within the range of the elements, then the stars have aligned and I can call memchar. I need to actually do a static cast here. I could go into why that's necessary. Then I need a static cast back out, and I need to do a little dance to adapt memchar semantics of didn't find something. It returns a null pointer to find semantics. That part is all simple. So how is within limits implemented? This is where it gets tricky. So let's go up here. This is actually a four-way, let's see, actually I can just stop debugging because I don't need any of this here. Okay, so I've got this within limits helper function, and it's going to be passed, here we go. It's passed the input iterator, which encodes the value type, and then the actual, the element type, and then the value type that I'm looking for. So I strip off a pointer, elem is my type, like signed char. And then I'm going to ask, okay, is elem signed and is tie signed? And these are two separate things. So I've got 4 possible cases. Signed elements, signed value type, or signed unsigned, and so forth. And then I've got this funny integral constant. So let's look at the usual arithmetic conversions now. Did I stop debugging? Yes, I did. Okay. So let's go to here and let's edit up a new file. Okay. So per CPP, and let's include IOStream and OStream. So I'm just going to do a little experimentation here. Suppose that I've got something like a signed char, SC, and this is initialized to -1, like in our repro, and then I've got an int I, and this is 255. Okay, and I would like to know, include ios, using namespace stood. ios gives me this cool thing, bool alpha. So then I can print bools. So hey, is SC equal to I? We know, just as programmers, that this answer should be false. So if I compile, static debug, per, and run per, please. Compile this to run. It says, hey, the signed char -1 is not equal to 255. So we just sort of intuitively expect this to be true. But as usual, C++ has to achieve this through rules that have no human emotion and no intuition. They usually, but not always, do what the programmer intends. And these are controlled by the usual arithmetic conversions, one of the few phrases in C++ that is deeply scary, along with one definition rule. So here we go. In clause 5, in this case paragraph 10 in the current working paper, it starts off in a relatively comprehensible way. I'll just read out loud. It says many binary operators, and in this case it could be like plus or equality, that expect operands of arithmetic or enumeration type cause conversions and yield result types in a similar way. The purpose is to yield a common type, which is also the type of the result. So in this case, and this was actually inherited from C, what the language says is if I've got some incoming type, like a signed char and maybe an unsigned long on the other side, I can't directly compare them. What I need to do is I need to potentially coerce them to a single common type, which could be the same as one of the inputs or different, and then actually do the comparison once the types are equal. This mirrors what's happening on the actual machine level, the metal, where you're emitting an assembly instruction that just takes two registers or whatever and then compares them. That's working on a single type. So C and C++ are doing the same thing because they're directly emitting essentially assembly instructions. So back to the standard, it says, this pattern is called the usual arithmetic conversions. And then it's just got a bullet list. So the first parts here about scope, denum, type, and then long, double float. I won't get into those. Those matter if you've got enumerations or floating point. Floating point itself is an area of extreme frightening rules. So we get down, and then it starts talking about integral promotions. So let's go back to my per. Now I'm going to get a little more fancy. Suppose that I've got something, okay, like an unsigned char x, and let's make it big. Let's make it something like 250. And then an unsigned char y, and let's make this like 200. Okay. And I would just like to print out, here I'm using IOStreams, which will automatically detect the type of the result. I'd just like to see x plus y. So as programmers, we expect x plus y to be 450. Now, many of us, especially if we've not stared at clause 5, can't quite express why that should be the case. But it's obvious, right? I mean, 250 plus 200 is 450. So let's compile and run this. And yeah, we get 450 printed. So that's awesome. But what if our values are slightly, or what if our types are slightly different? Okay, so let's have an unsigned long. And here, another unsigned long. Okay, and let's make this big. I'm going to print this in, let's see, I can print as an integer. So I want 4 billion. Okay, and I'm going to actually encode this constant as unsigned long. Unfortunately, I do not have decimal separators, so I actually need to crunch out these spaces. And let's suppose this other one here is something like 3 billion. Let's make it, we can make the first one tiny. 3 billion plus 4 billion as unsigned long. So both of these numbers are within the range of an unsigned long, which on our platform is 32-bit and go up to like 4.2 billion. So if I add them, what should I get? Should I get 7 billion? Well, the answer is no. Let's see what this prints. Okay, so let's type per, and then compile per. And the answer is no, I do not get 7 billion. Instead, I get 2.7 billion and some change. So that's weird. Why, when I added unsigned chars, when the result 450 was outside the range of unsigned char, how come I just got that without being modified in any way? Yet when I try to add unsigned longs, here I actually wrap around, and I don't get 7 billion widened to like 64 bits, I get 2.7 billion. This is kind of weird. And the answer is the usual arithmetic conversions. So let's go here and see what happened for those unsigned chars when I added them. Okay, so it's got this bullet points about scope denum and floating point, and all of that is false, so we get down here. It says, otherwise, the integral promotions shall be performed on both operands. So that's cool if you know what integral promotions are. But say we don't. Let's go to clause, or section 4.5. Okay, and this whole section is dedicated to this thing called the integral promotions. And this first one is actually the important one. And it's got some bit about PR values. We can just ignore that. It says a PR value of an integer type other than bool, char 16, 32, or wchrt, whose integer conversion rank is less than the rank of int. Okay, so let's stop there. What is this talking about ranks? Well, I can skip here and just tell you that anything with the rank less than int means a tiny type. That means chars, signed and unsigned, shorts, signed and unsigned, and that's it. I don't think I'm forgetting anything else. So any of those tiny types can be converted to a value of type int if int can represent all of the values of the source type. Otherwise, blah, 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 and that does not actually apply on VC's platforms where int can actually always represent those values. So let me sketch out something here. I guess I can erase this doom here. The doom is still present, I just need the space. Okay, so if I've got something like an unsigned char, okay, this is a value in 0, 255 inclusive, and int on our 32-bit platform can represent negative 2 to the 31st, and then 2 to the 31st minus 1. Hopefully I'm not getting that wrong. So this is totally within this gigantic range. And if I've got signed char, which is from negative 128 to 127, again assuming 2's complement, which is true on our platforms, totally within this range. Unsigned short, that's 0 to 65K, also within the range of it. Signed short, from negative 32K to 32K, also within the range of int. So what this is saying is, unless your types are like really weird sizes and the standard is written to accommodate those platforms, things like chars and shorts, they just get widened to int as soon as you pass them to binary operators like addition or equality. This is very interesting. And the reason why is, again, it goes back to C. If you think about, back in the 70s when C was designed, we're going to emit assembly instructions, and the natural width of the machine int, in those horrible days it was 16-bit, all the instructions are going to work on ints anyways. So if we've got a type that's like a single byte, we may as well just widen it to int, because that is what the machine is going to execute on. So this is exactly what allowed me to take an unsigned char of 250 and an unsigned char equaling 200 and add them together. And what happened is the usual arithmetic conversions said, okay, you are tiny types, you are unsigned chars, I'm going to promote you to int. So they got promoted to ints, and then I add the 2 ints, and then it's not surprising that I get 450. They do not remain unsigned chars even though they started out that way. So that is actually desirable in most cases. You start with these unsigned chars and you get the value adding them preserved without wrapping around to something less than 255. In fact, it's so natural that we just sort of always expect it when we work with types. We're not constantly on our guard. And so that is nice. And the thing about the usual arithmetic conversions is that they often produce intuitive results, except when they don't. Okay, so otherwise the integral promotion shall be performed. So after tiny types have been widened in it, we just proceed on through these usual arithmetic conversions. It says, then the following rules happen. So if they both have the same type, then we're done. This is awesome. This is what happens if you like add 2 ints, or add 2 unsigned longs, or add an unsigned char and a signed short. So let me walk that out on the whiteboard. So what if I've got something and I could say static cast, blah, blah, let me just talk in terms of the types. Imagine I've got an unsigned char, and then some binary operator, could be plus, it could be equal, equal, it could be times, whatever. Something like a signed short. I'm just always going to explicitly write this out. Even though in real code I would never say sign there, except for chars. In this case, what happens is, first, the usual arithmetic conversions say, okay, you're not enums, you're not floats, okay, you get promoted. Everybody gets a promotion if you're tiny. So char gets promoted to int. Signed short gets promoted to int. And then the bullet points activate and it says, oh, these types are the same, I am just going to add them or test them for equality or multiply them or whatever. So even if the types are different, after the promotions, if they're identical, then they just proceed on without further modification. Okay. And remember that the integral promotions, they preserve values, because there was that standardese there about they're widened to int only if int can represent all of the values. But then we've got other bullet points. What if the types aren't the same, even after the promotions? So then it says, otherwise, if both operands have signed types, or if they're both unsigned, then the littler one gets converted to the bigger one. So this is also kind of intuitive, and it actually produces expected results. Imagine, okay, now I need to have big types that won't undergo the integral promotions. Imagine I've got something like a signed long. Okay, maybe say this one is negative 2 billion. Okay, that's a totally reasonable value. And imagine that I'm also going to, say, add it to a signed long. okay, whose value is something like negative 7 billion. Okay, I add these together. So they go through the integral promotions, and this says, okay, you guys are big, so I'm not going to promote you. Then it says, okay, are you the same? No, they're not the same. So then it hits this bullet point about if they're both signed, which they are, then the littler one gets promoted to, or sorry, gets converted, I should not say promoted, to the width of the larger one. So what happens here is that signed long will get converted to unsigned long, which is 64-bit. That's value preserving because it's just totally bigger. And then they get added, and we end up with negative 9 billion as expected. So this is intuitive. If I take a signed long and I add it to a signed long, I sort of expect I'm going to end up with a signed 64-bit. So that's cool. But then the usual arithmetic conversions, sort of the clause come out. It says, okay, otherwise, if the operand that has unsigned integer type has rank greater than or equal to the rank of the other operand, then the signed one gets converted to unsigned. This is where the fun happens. And then it says, otherwise, if the type of the operand with the signed integer type can represent all the values of the type of the operand with unsigned integer type, the unsigned one gets converted to the signed. So all these signed, unsigned, they're all flying around. It's not clear what's happening. This is scary because these conversions can transform values. And when you get a value transformation, that is deeply unintuitive to almost all programmers. In some respects, it would have been better if after the integral promotions and this bit about them both being signed, after all of that, if the standard just sort of stopped and said, oh, otherwise you need to explicitly convert with a cast, static cast or even a C cast, otherwise these types are just incompatible. Now, C and C++ didn't do that. And the reason why is, remember how C was designed. It assumed that the programmer knows what they're doing. And it also assumed that they really, really want their code to compile. They don't want to have to be very explicit about all sorts of things. That's why we've got all of these conversions. And it's great when it works. The problem here, as you sort of work with this over time, is that it's so desperate to compile your code that when it does things like value transformations, it can actually produce unexpected results if you're not deeply familiar with the usual arithmetic conversions. And by now, it's far too late to change this. I mean, if these rules were tweaked in any way, aside from something like adding 64-bit types according to the same conventions, we would just break all C and C++ code throughout the world. The value of that is actually greater than the headache of dealing with this every once in a while. So that's why the rules are the way they are. And this is also why we have compiler warnings. You will see compiler warnings about, oh, you're comparing a signed type to an unsigned type, and this could potentially do blah, blah, blah. So that's why those compiler warnings exist. They can't catch all cases, but they are helpful if you've ever wondered why you've seen one of those. Okay, so essentially, once we get here, and the scary rules, if you just want to remember them briefly, the scary rules are when you're working with types of different signedness. Because if they're both signed, or they're both unsigned, then things aren't going to go very bad. Whereas if you're mixing signedness, things are crazy. Okay, so let's go back, all the way back, popping many things off the stack, to this within limits function. So that's why I'm testing is signed LM versus is signed tie. I need 4 different cases, because what could happen if I've got a signed element versus an unsigned tie, blah, blah, blah. So I've got 4 overloads here. Let's look at the simple ones. So I start off, LM is on the left. So imagine I've got signed elements, true, and a signed value that I'm looking for, true. Okay, in this case, if I work through all the rules, and it actually took me quite some time to look through all the possible cases and figure out exactly what could happen. In this case, there are actually no bizarre value transformations, and I just need to do 2 bounds checks. If this value is within the range of signed char min and signed char max, this is negative 128 to 127, then it could possibly match within this range, and I need to return true. If it's outside that range, then I need to return false, saying, hey, there's no possible way this could exist. Don't call memchar, just return the last iterator. So that's cool. Skipping over some interesting things. Okay, so if I've got 2 unsigned values, so I've got an unsigned char as my element, and then I'm looking for an unsigned value, like another unsigned char, or an unsigned int, or an unsigned long. If I work through all of these things, again, there's no value transformations. So all I need to do is see whether they're within bounds. I know they're both not less than 0, because they're unsigned. I just need to do an upper bounds check. So if the value is less than or equal to 255, then okay, proceed onwards to memcare. Okay, then things start getting trickier. Remember how I said that mixing signedness is where things start to get a little freaky. If I have an unsigned element, like an unsigned char, and then a signed type, so I'm looking for something like int or long or something big, what could happen? So let's actually work through what the usual arithmetic conversions say. Okay, so in this case, I want to know for the purposes of for find its equality, but the actual binary operation doesn't matter because the usual arithmetic conversions, that's a mouthful, apply to essentially most binary operators. I don't want to say all. Okay, so if my element type is, now I've gotten unsigned, so I've got unsigned char. Okay, here I'm just thinking about the type. I've got this whole range, and these things are all in the range 0 to 255, but I don't know at first what they could possibly be. I just know the range. And then the thing that I'm looking for is signed. That's what my template metaprogramming has detected. So I've got some signed t. Okay, and t could be, it could be tiny, so I could be working with signed char, it could be signed int, it could be signed long. All I know is that it's signed and it's integral, so I don't need to worry about like doubles or strings or anything bizarre. I want to know, is this possibly within the range here? So I would love just to be able to test against these two bounds. I need to see, okay, is this thing negative? If so, it can't possibly be equal to an unsigned char. Or is this thing positive? But I want to know, when I do those tests, am I going to get these bizarre transformations? So if I work through these rules, let's look at the usual arithmetic conversions now. There's a whole bunch of corner cases. I could talk for hours about this. So if you see me skipping anything, I assure you that I have actually reasoned about all of this as precisely as possible when I wrote this fix. Okay, scope denums, doubles. Okay, so integral promotions. The integral promotion shall be performed on both operands. So what does this do? Unsigned char is always tiny, so this will become int. This gets promoted. Okay, then the signed t gets promoted. So we could have signed char, signed short, signed long, signed long. And by the way, we could also have signed int, which on our platform is the same. Width is long, although it's slightly less rank. These get promoted. So chars and shorts get smashed to int. So after promotion, we end up with a signed either int, long, or long. Okay, so that's interesting. And we know this int on this side is 0 to 255. Then we do a comparison. So, okay, after the promotions, it says, okay, if both operands have the same type, no further conversion is needed. And by the way, this one was value preserving, so this one's good, because int can totally represent the values in 0 to 255. And the integral promotions from signed char and signed short to int, we know those are also value preserving. So we're not going to be changing any numbers. The other thing that I've been sort of assuming without explicitly mentioning it, that's probably a good thing to mention. It is really important in C and C++ to distinguish between values and representations. So a value is just a number. It's a mathematical number, like 5 or negative 127. It's a number. A representation is a bunch of bits. And that's because we're working on computers whose states are signaled by electrons versus not electrons. So that's why we've got to need to represent things with bit patterns. For unsigned, it's very simple to see. For signed numbers, everybody uses 2's complement by now, even though the standard says you've got a couple other possibilities. These things are distinct, and I keep mentioning value preserving. So when we convert types, if it's value preserving, that means 5 as a signed char will be preserved 5 as a signed long or long or whatever, even though a signed char is only 8 bits wide and a signed long is 64 bits wide. So different representation, but the same value. Whereas if I get a value transformation, that means that in addition to messing with the width of the bits or whatever, or the meaning of the sign bit, I'm also changing the value that it represents from, say, -1 to 4 billion. That's a value transformation. So value preserving on this side, and then when I promoted these, this was also value preserving if it happened, otherwise I didn't even mess with the type. So far we're good. Okay, so if they both have the same type, no further conversion is needed. So if the one on this side was assigned char, assigned short, or assigned int, then these all get smashed to int. That's the same here, and we directly compare them. Nothing crazy happened, no value transformations. Otherwise, if both operands have signed integer types, the one that's tinier gets converted to the one that's bigger. So that happens if the one on the right is either signed long or signed long long. In that case, the signed int gets widened to potentially long or long long, which 32 or 64. And that, again, is value preserving. So this is good. This means the stars have aligned, they've smiled on us, and even though the types here are different and we had to work through a bunch of rules, nothing bizarre is happening. So that's why, if I debug in here, I can just do two comparisons. I compare my value, which is one of these things, against the constant 0 and uchar max, seeing, okay, is this value less than 0? Oh, you can't possibly match an unsigned char. Are you bigger than 255? Again, you cannot possibly match. And I know that when I compare this signed value against these constants, these comparisons themselves will not behave bizarrely. Okay, so now let's get into the extremely fun case. Here we go. Okay, so the case here, which is actually suspiciously similar to the one that prompted the bug. Out of 4 cases, only one is special, is when I've got a signed element. So I've got a signed char. Okay, and then I've got an unsigned type. Okay, again, this could be char, short, long, or long, long, but they're all unsigned. Okay, so my signed char, I know I'm in the value range negative 128 to 127. Okay, and we know the integral promotions will immediately promote this on site to int in a value preserving way, so that's cool. And then unsigned t. So what happens if I compare, and here I've got actually a sub case, what if I've got unsigned char, this is getting tiny, or unsigned short? Okay, so these get promoted because they're tiny to int. Value preserving, and then we just compare them. Okay, so this is normal. We would see that something like 255 is not equal to any number in this range because this one gets widened to int, and then in ints we can totally compare such tiny numbers and nothing bizarre happens. Same with shorts. So in this case, and I actually detect with the static cast, I'll get into what this is really doing in this other one. What do I need to do? So I know this unsigned value, it's unsigned, so it's certainly going to start at 0. But I don't know how big it is because I have not actually detected whether it's char or short. So I know it can't possibly be too negative. That's easy. This one falls in the middle. But I do need to test, is it too big? Is it like 255? Or, you know, even 150 would be too big. So I need to do a single test to see, okay, is the value less than or equal to 127? If so, I'm within bounds. But then why do I've got this other thing here? I had mentioned at the beginning, okay, I've got a possibly signed or unsigned element. I've got a possibly signed or unsigned value that I'm looking for. That should be 4 possible cases. Yet I've got 5 overloads of within limits. What is going on here? This is where the usual arithmetic conversions get extremely fun. Okay, so let me erase this. Okay. So what if I've got an unsigned t here? Again, I've got signed char on this side. What if I've got an unsigned t that's unsigned int or long or especially long long? These are huge, huge types, like 64 bits. That's enormous. Who could ever need more than 64 bits? Okay, what goes on here? Let's look at the usual arithmetic conversions, although you can see from this overloads I'm definitely doing something interesting. Okay, not enum, not floating, integral promotions. Signed char promoted to int, value preserving, good. This other thing is unsigned int, unsigned long, or unsigned long long. That's bigger than int. So it is not going to get promoted. We don't mess with it at all. Okay, so next bullet point. If they both have the same type, we're done. But they're different. This is signed int, and whatever this is, it's unsigned int long or long long. Totally different types. So this bullet point does not activate. Next bullet point, otherwise if they're both signed or both unsigned. No, this one is signed int and this one is unsigned something. Next bullet point. Okay, so here it says, otherwise, if the operand that has unsigned integer type, so that means this one on the right-hand side, notice how the usual arithmetic conversions are specified just in terms of the types. The left and the right are not special. The only reason I'm distinguishing left and right here is because of how std_find operates, where the element is always on the left and the value is always on the right. But if the sides were reversed, the conditions would be exactly the same. Okay, so if this unsigned type has rank greater than or equal to the rank of the type of the other operand, then blah, blah, blah. So is this true? Yes, it is, because the rank here, this thing is either unsigned int, unsigned long, or unsigned long, long. These things are all equal to or bigger than this int here. So this bullet point does activate. Okay, and it says the operand with signed integer type, so that means this one, is converted, shall be converted to the type of the operand with unsigned integer type. So it's saying in this case, the programmer, and this goes all the way back to C, if the programmer is starting with a signed char on the left, and they've got an unsigned int, unsigned long, or unsigned long, long on the right, then what I'm going to do is I'm going to promote to int, then I'm going to convert this to the type of the other operand, and then actually do the comparison. So what does this do? Okay, if my signed char is in the range from 0 to 127, okay, then when we convert int to unsigned int, unsigned long, or unsigned long, long, this is value preserving. This is an unsigned thing, it's a whole bunch of bits, we fill in a bunch of zeros, and then we copy the int here, and we're done. So 0, 127 gets mapped, now thinking just in terms of values, to 0, 127. Okay, that's cool. But what if, I'm going to red here, actually I can erase this. What if the value on this side starts off being anywhere from negative 128 to negative 1? Okay, these things are all negative. These values cannot be represented as an unsigned anything. So if I do such a conversion, I must get a value transformation. And in a 2's complement world, which is what our world is on VC and essentially all other platforms, this is bit pattern preserving, although not value preserving. So, for example, negative 1 here gets mapped to F, 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 blah, 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 8 Fs. So all 1 bits as an int or long or long, long. So 8 Fs or 16 Fs. That sounds right. And negative 128 would get mapped to F, F, blah, 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 80 in hexadecimal. So this is the same bit pattern if you look up Wikipedia how 2's complement works, but these are totally different values. What this is saying is you take a negative 1 as a signed char, promoted int, and then converted to this unsigned thing, and the value negative 1 gets changed into either 4 billion or 18, however many quadrillion it is, 2 to the 64, or slightly less if it started off being like negative 127. So that is interesting. What does this mean? Well, let's look at here. Okay, so we know that these values will be warped over. Let me go to my little example here where we can test out things. Okay, this is deeply, deeply surprising. So if we didn't know this, we might be tempted to say, oh, we can just do the same thing. We know that an unsigned value is going to be 0 or bigger. So we just need to compare this thing and see, is it less than or equal to 127? And if so, you're within range and you're good. Because I know that if you're larger, this unsigned value, if you're larger than 127, you cannot possibly match. Yet, there's this whole thing going on with negative numbers here. What does that mean? So imagine, this is an exception to the rule that I've been using everywhere else. Because of usual arithmetic conversions, imagine I start with the signed char, SC, and let's say it's negative 1. Okay. And then let's start with an unsigned long, long. Let's just really emphasize how big it is. Unsigned long is fine. UL. Okay. How big is this going to be? OX, 1, 2, 3, 4, 5, 6, 7, 8, unsigned long, semi. There's rules about what happens if you omit the suffix here. I can never remember them. I always slam on UL if I want to know. Okay, so is the signed char negative 1 equal to the unsigned long 2 to the 32 minus 1? So let's see, is SC equal to UL? Let's save and compile. and run. Needless to say, even though I'm using Milan here, this is the same in all VCs forever. First, I get a warning. It says, hey, signed to unsigned mismatch. Something funny might be happening here. Then it tells me, oh, -1 is equal to 4 billion, blah, blah, blah. So that's funny. Why did that happen? It's because of the usual arithmetic conversions. -1 promoted from signed char to int got slammed over to an unsigned long, and that changed its value while preserving its bits. And then after all of this conversion, -1 became FFFFF, and that's equal to FFFFF on the right-hand side. So that's interesting. Going back to find, which is what I'm really interested in, this means I need a very special test in addition to a compile time test. So here I've got the range of possible values, -128, 127, okay? And then I've got an unsigned t. Okay. The question I want to ask is, could this t possibly match a signed char over on this side, promoted to int? So if my value is in the range 0 to 127 here, this could possibly match. 0 to 127 matches this half of the range. That's cool. 28, -1, and 0, 127. So if this thing on the right is in 0 to 127, then it could match. I don't know if it will, based on the elements, but if it does, or if it could, then I need to actually call memchar. Also, if the thing over here, which is unsigned, so it's just unsigned, I'm going to write it out as hexadecimal. If this is huge, if it's in the range FF80 to FF all Fs, so the biggest possible number is an unsigned, then working through the usual arithmetic conversions, these enormous, enormous values will actually match the tiny numbers -128 to -1. So I actually need two tests, and not just a single, am I within a single range? I need a split test. I need to see, okay, unsigned t, are you super duper tiny or are you super duper huge? And if so, you could actually match over here. Otherwise, I would get answers wrong, because remember how find is specified. It says, if I went back to find, it's specified in terms of equality. So if the usual arithmetic conversions say that -1 signed char is equal to FFFFF unsigned long, std find had also better agree with this interpretation, even if I'm calling memchar. So going back to this implementation, if the stars aligned, I'll show you how I did that, then I need a two-part test with an OR. I'm saying, okay, if the value here, this unsigned thing that's big, if it's less than or equal to 127, then I know I'm in this half of the range and things are cool. Or if I'm enormous, if signed char min, so this is -128, cast over to FFF80 with the static cast. If val is even bigger than that, then I know I'm in this upper half and I'm going to be equal. So that's what this is testing. And how did I get here? Remember how I said that this case only activates when the t is big, because that prevents it, this t from going through the integral promotions. I could have explicitly encoded unsigned char and unsigned short for special treatment versus unsigned long and unsigned long. But instead, I wrote a simpler test. In my helper here, I said, okay, let's call this helper within limits, give it the value, tell it is the element signed, tell it is the type signed, and then for this very special thing, I can detect when this will happen, possibly happen with this value transformation here, if -1 as a signed char promoted in, so I could just say int, is equal to FFFF as an unsigned t. Okay, so the question I want to ask, is -1 the int? I don't need to say signed char because that would just get promoted on site. Would this be equal to -1 static cast to tie, which is unsigned? So this would be FFF enormous. Sometimes this is false. This is false when this type here is small, like unsigned char or unsigned short. But if it's big, then stepping out at a high level, the usual arithmetic conversions say this thing is so large, it sort of has a gravitational pull, and it's going to coerce the other type, the integer, the signed integer, to be converted to an unsigned large type. So when this is true, then I need this special split two-part test. And with all of this logic, and look what happened here. I've got my stood find here, it's got some debug checking, and then it calls this internal helper. It's got some metaprogramming here to see, okay, is the element type and the value type I'm looking for eligible for the memcare optimization? If so, then let's call this one here, otherwise go back to the generic algorithm. And then within the memcare optimization one, do this limits test, and that does 4 possible combinations of signed versus unsigned, and then add a 5th one for when the large right-hand side could cause a value transforming conversion in the usual arithmetic conversions. So 5 overloads of within limits. Then do a value test, and then if it's possibly within range, call memcare, adapt, and blah, blah, blah. All of this is necessary for both correctness and performance. Oh, and by the way, integral types include bools. Yeah, you can totally pass a bool to find within and look for something in a range of unsigned care or short. This triggered compiler warnings that I could have worked around, but it was easier just to add a overload for bool and just say, oh, bool, which is 0 or 1, interpreted as an integer. That's always within the range of a signed care or unsigned care. So that's why I've actually got the 6th overload that's not super important. That's what all of this machinery is doing, and it exists to work around, essentially, the behavior of the usual arithmetic conversions. And this is necessary to adapt stood find semantics over to memcare semantics, which is potentially faster than the core language. So what does this mean? What does this mean for you? Because you're probably not implementing stood find yourself. What this means is that if you're not concerned about correctness in all possible cases, you usually don't have to worry about this stuff. Because if you're working with reasonably sized types and you're not mixing like signed and unsigned, everything essentially works. This is why this doesn't blow up for programmers on day one. However, as soon as you start mixing signed and unsigned types especially, or if, like stood find, you're implementing a generic algorithm that is going to modify, work with integral types, and potentially convert them or compare them or add them together, if they could trigger the usual arithmetic conversions, you really should know these rules because the promotion, they preserve value, and the thing about widening types of the same sign, that preserves value. But as soon as the usual arithmetic conversions say, okay, I am so desperate to compile this code, I need to convert unsigned to signed or signed to unsigned, that could potentially modify values. Both directions can modify values because converting large unsigned numbers to signed numbers, that could actually produce negative values. I think that's actually implementation defined. But on a 2's complement machine, that's what will happen. And vice versa, we saw here, converting a negative number to unsigned, that can change a negative number to an extremely large unsigned number, and that is often unexpected. So if you're aware of this stuff, then when you start writing code that could potentially trigger this stuff, you'll hopefully remember it and then take care to either work around it by maybe casting the values. Remember, casts are dangerous, but if you know what they're doing, they're useful to silence compiler warnings, or work around it, just completely avoid it by starting with types that are the same signedness or the same width. Because remember, if the types coming in are both identical, then you don't have to worry about any of this stuff because the usual arithmetic conversions say, oh, after promotion, if they're identical, hey, I'm done. It's only when you start mixing types of different widths and especially different signedness that these interesting rules come into play. And these exist, for C compatibility, and they're good, but they are occasionally a source of headaches, as you can see in this sort of code. So that was part 7, and like I mentioned, this initializer list aware libraries will be coming to you at some point in the future. Can't say when yet. So let me know in the comments if you have questions about the usual arithmetic conversions or anything else you'd like to see. Until then, see ya.